everybody, it's Miss List, and I'm here today with 3.7 solutions and mixtures. Even though solutions can come in any phase of matter, for example, air is a gaseous solution and alloys are solid solutions, we focus mostly on liquid solutions in chemistry because that is the most common type. For liquid solutions, the solute may be a gas, liquid, or solid, and while there are many different ways to describe solution concentration, molarity is the most common concentration used in the laboratory. Occasionally, you might see something called molality referenced. You can also measure concentration in parts per million or parts per billion. Again, those are all things you might see if you continue your chemistry studies and science studies in general, but for us in lab, the one we use the most is molarity. So molarity is moles of solution. Molarity is moles of solute over liters of solution. So this is going to be N, the number of moles, divided by the liters. And we can also remind you of when we do a dilution, we often use M1 V1 equals M2 V2, where M1 and V1 represent the initial solution. Sometimes the initial solution is called a stock solution, and M2 V2 are the diluted solution. The reason that we can make this equation work is because when you dilute, the number of moles stays constant. And if number of moles stays constant, you can get molarity times the volume and then set those two equations equal to each other. Some properties of liquid solutions is that when we have a solution, we can't separate the contents by filtering. Filtering only works if I have something that is undissolved. There are no components large enough to scatter light, and that's called the Tyndall effect. If you want some cool videos, you can Google that. But essentially, if I have a solution and I shine a laser through it, I won't see, if my laser is going this way, it will start, and I'll actually go to a different color here. It will start, so those are my initial laser beams, and then it will come out on the other side, but we don't see any light there in the middle, and that's because the particles are so small and so evenly mixed that they are not going to show up and scatter light. For ions that are dissolved in solution, it's important to note that ionic compounds completely disassociate, and that term disassociate means that they 100% break apart. And because of this, the concentration of ions can be different. It's not necessarily going to be the same as the original solution or the original molarity. Here's an example of what I'm talking about. On the left, I have sodium chloride. So if I have a 0.1 molar solution, that means because sodium and chlorine breaks apart in a 1-to-1 ratio, that means I'm going to have 0.1 molar of the sodium and 0.1 molar of the chlorine. However, if I compare that to calcium chloride, if I have that same 0.1 solution, calcium chloride does not break apart in a 1-to-1 ratio like sodium chloride does. For every 1 calcium, there are 2 chlorines. So if my original molarity is 1 molar calcium chloride, that means that the calcium is going to match that, because they both would have a coefficient of 1, but I'm going to have twice as much because of this coefficient of 2. I'm going to have 0.2 as the concentration for chlorine. So we really have to be careful when we're dealing with, specifically if they ask for the molarity of an ion in a solution, we really have to think about how does that break apart. Is it a 1-to-1 like we saw with sodium and chlorine, or is it a 1-to-2 ratio like we see with the calcium chloride? All right, so let's look at some example problems. It says a student used a 50 milliliter burette to add potassium permanganate to vinegar until a faint lavender color was observed in the flask, an indication that the end point of the titration had been reached. We'll talk more in Unit 4 about titrations. The initial and final volumes of the readings of the solution are shown to the right. What volume of KMNO4 was added during the titration? So when we read burettes, it's a little tricky because the numbers are inverted. So this would be 3.1, 3.2, 3.3, and it looks to be right on the 3.4 line. And when we're reading volumes, especially off burettes, you know it's exactly 3.4, and the last digit, because we always estimate one additional digit, if it's exactly on the line, I would call that 3.40. If it was a little bit above that line, I might estimate it to be slightly different. So I'm going to say that this burette is reading 3.40. The final burette, we start at 29, and so this line here would be 29.5, and this is 29.6. And remember, we want to read from the bottom of the meniscus. It's kind of hard to see without me zooming in, but it does appear that that line is not exactly on the next line. So I might call this 29.6, and then it looks like maybe it's just a little bit over the 26.6. It looks like it's just a little bit over the 29.6 line, so I might call that 29.65. And that is my final. So if I want to know how much was actually added, I'm going to subtract those two numbers. I'm going to go 29.65 minus 3.40. When we subtract for significant digits, we use the number of decimal places. So I'm going to keep the number of decimal places that I have, which is 2. And I get that 26.25 milliliters were delivered. Next, it says determine the moles of KMNO4 that was delivered if the molarity is 0.320. So again, molarity is moles over liters. They gave me the molarity as 0.320. I'm looking for moles, and then I just found the volume in part A, so I'm going to put that as 0.02625. And then to solve this, I'm going to multiply both sides. That will cancel. Again, I put my volume into liters. That's why it's 0.02625. And then I can multiply these two numbers, and that's what's going to give me my moles. So I go to my calculator, 0.02625 times 0.320, and I'm going to keep 3 significant digits. I get 0.00840. Next, we have a student dilutes 100 mils of 0.2 molar calcium chloride to a final volume of 400 with distilled water. They want us to determine what is the molarity of specifically the chloride ion in the 100 ml solution, which is my initial. So remember, and we talked about this a second ago, calcium chloride, for every 1 calcium, we get twice as many chlorines. So if this is a 2 molar solution, calcium is going to be 2 molar, but we have twice as many chlorine. So in that solution, I'm going to have a concentration of chlorine as 4 molar. Now we have to do a dilution. So they say that our initial solution, the more concentrated one, was 2. We want to know what will the new molarity be if I dilute it to 400. And for this one, because the number of milliliters end up canceling, you can leave it in mils. You do not have to change it into liters if you're doing a dilution. So to simplify, 2 times 100 is 200 divided by 400. That means my new molarity is going to be 0.5. So if we take that same concept from the first one, we have 0.5 molarity, which means calcium will be 0.5. but the chlorine ion is going to be twice as much. So our chlorine ion is going to have a 1 molar. Okay, so in number 3, they say that a 100 ml sample of 0.5 NaNO3 is mixed with 100 mLs of a 0.5 molar solution of calcium nitrate. And they want us to find what is the final concentration of the NO3 ion. So remember, concentration is moles per liter. Well, we know that the solutions are being combined. So we're adding 100 mils and 100 mils. So the volume is going to be 200 mils. What I need to figure out is how many moles this is going to end up being. So for the sodium nitrate solution, I need to figure out how many moles this is. So I'm going to use my molarity equation using the information they gave me on the nitrate solution. And I'm going to multiply both sides by 0.1, and I get 0.05 moles. If we do a similar thing on our other solution, we're going to get the same value. The difference, though, is that we have twice as many nitrates here. So even though we get a 0.05 moles, remember that we have 2 nitrates. So really, I need to take that by 2, and that's going to be 0.10. Now that I have the number of moles of each solution, the 0.1 and 0.5, I can put those together, and that's what's going to go in the top of my molarity equation. So I'm just going to come over here because I'm kind of out of room. 0.15 moles divided by 0.2, and I would get a molarity of 0.75. Next, we have how many grams are needed to make 10 mLs of a 0.5 molar solution of calcium carbonate. And they conveniently gave us the molar mass here, and so that actually makes our calculation a little bit faster. So first, I'm going to see how many moles this is. 0.50 equals moles. And then 10 milliliters is going to be 0.010 liters. So I'm going to multiply by 0.01 on both sides. That cancels. Whatever I do on one side, I'm going to do on the other side. So 0.01 times 0.50, and I get 0.005 moles. And then to get that to mass, I am going to multiply by the molar mass. Remember, the molar mass is in grams per mole. Moles and moles cancel. So that's going to end up being about 0.5 grams. Final question here, it says describe the equipment a student should use to prepare 100 mils of a 0.250 molar solution of sodium hydroxide using the equipment from the list. So first we're going to do our calculation because I need to know how many grams of sodium hydroxide I need to measure out. So I'm going to do a similar calculation to what I did on the last problem. I have my molarity equals moles over 0.1. 0.0025 is 0.025 is going to be the number of moles I have, and I'm going to figure out how many grams that is by multiplying by the molar mass of sodium hydroxide. Molar mass of sodium hydroxide is around 40. So I'm going to take 0.025 times 40, and I actually get 1 gram. So how can I describe how to make this solution? First is I'm going to measure out 1 gram of NaOH solid using a weigh boat and scoopula. Then I'm going to transfer the NaOH solid, and this is a big one. We're going to transfer it to the 100 ml volumetric flask. We only ever make solutions in volumetric flasks because it is the most accurate. Graduated cylinders are second best. We would never be making a solution in a beaker because they are not accurate at all. If given the option, we should always choose volumetric flask to make our solution. Step 3, we're going to add just a little water, and we're going to swirl until the NaOH solid dissolves completely. And then this is the final step with a volumetric flask. It's the one that looks like this. We don't have lines going all the way up. We only have one line. And so initially we put a little bit in here to swirl and dissolve our solid, but now we need to fill it the rest of the way up with water. So we are going to now add water until the meniscus bottom is on the 100 ml line. A common mistake that students say is you would just add 100 mils. And if you add exactly 100 mils, that's actually going to take your volume above the 100 ml line, because your pellets, the solid NaOH, actually takes up space. So this is really the preferred way to say it, is that you're going to add water until the meniscus, or the bottom of the meniscus, is on the 100 ml line. You're not adding 100 mils, you're adding up to the 100 ml line. All right, and that's all I have for you today. I'll see you next time.